Hi, this is an example problem from Chapter 22 on calculating magnetic flux. Pause for a moment to read the question. So in this question, it says that we have a magnetic field and we have a circular surface with a given radius, and that the orientation between the magnetic field and the normal to the surface is given as an angle. This phi equals 25 degrees. Part A asks us, what is the magnetic flux? Capital phi, turns out. Those are different. Distinguish those two. What is the magnetic flux through the surface? So to start this problem, we need to figure out how to visualize this. Since the magnetic field direction hasn't been specified, we're free to choose that direction, but we have to orient the circular surface so that the angle phi, 25 degrees, is accurate. I've gone ahead and drawn a picture of this. So here's a picture, and I've decided to make the magnetic field point straight upwards. And notice how I've taken this loop and I've oriented it so it's tilted 25 degrees above the horizontal. Now this circular loop, I kind of twisted it a little bit so you can see it's three-dimensional. Really, it's just kind of like a knife edge that you'd see, of the loop, but we want to kind of see the whole surface there. Now, what is this normal line here to the circular surface? Normal means perpendicular. You remember the normal force, that was perpendicular to the surface in Physics 2a, right? In this case, that means I'm going to draw a line that's perpendicular to the surface of the loop. This is our normal line. Sometimes we call it a normal vector. Put a little arrow on it. And the magnetic field direction, well, we know what that is. I'm going to draw it in purple here. Looks like that. Right, there's our magnetic field vector, right? Tangent to the magnetic field lines and oriented in their direction. And so this angle phi that we're trying to figure out here, this guy, that is the direction, or that is the angle between the direction of the normal line and the B field. So here's our phi. And it turns out that that is also going to be 25 degrees based on the geometry. Now again, what is the idea of magnetic flux? Well, let's write down the equation. So here's the magnetic flux. Sometimes I write phi sub b here for magnetic. And it's equal to the magnetic field strength, magnitude, the area of the loop, multiplied by cosine of this angle phi that we just talked about. And the idea of magnetic flux is something that passes through a surface. Magnetic flux is the amount of magnetic field lines passing through the surface. We can see in this case, it's tilted, so we're not getting the total surface with magnetic field lines passing through it as much as possible because of the tilt, but we are getting, some lines. These guys go through it. And so the orientation matters. Let's go ahead and calculate what this is going to be for part A. So the magnetic field strength is given. 0.078 Tesla. The area of the loop is given. Let's see, it's not given as a radius, but we know the area is going to be pi r squared, and the radius is 0.10 meter squared. The formula for the radius, for the area of a loop of radius r. And finally, cosine of the angle, 25 degrees. So we end up with a value that's equal to 2.22 times 10 to the minus third. And what are the units here? Well, we can see that this is going to be Tesla times meter squared. So that's the units for magnetic flux. We also call this a Weber. So a Weber is the same as a Tesla times meter squared. Let's look at part B. If the magnetic field is then removed, say by turning off the say by turning off the electromagnet, this should say magnet, producing it, what is the change in magnetic flux delta phi? So we're imagining that maybe this magnetic field is generated by a solenoid below. If we turn that solenoid off, we can get rid of the magnetic field. Now what's the flux through the loop? Well, it's going to be 0 because there's no magnetic field passing through. So this is an easy one to do. So I'm going to call this theta final because we turned off the magnetic field now. It was on before. So now we got B final times A times cosine theta. We haven't changed the phi angle or the area, but we've turned off the magnetic field. So this is 0, which means that we get a value of 0, right? Now that's not what we're asking for to calculate in part B just yet. We actually want to know what is the change in magnetic flux. So let's call this the initial value when the field was on, and the change in magnetic flux, delta phi equals phi final minus phi initial is equal to 0 minus 2.22 times 10 to the minus 3rd Webers. And so we're just going to end up with this number here. The reason why we focus on the change in magnetic flux is because it plays the important role in Faraday's law, which determines whether we have a induced EMF or not. Now, the idea here that this is a negative value is simply the idea that a couple things. So when we look at the picture, we've decided by making the normal line in this direction that if you have magnetic field pass through in that direction, then we're going to have positive magnetic flux. If instead the magnetic field went down in this direction, it would be negative magnetic flux. And since it started with a positive value and it went to 0, the change was to go from high to 0. It's a negative change. So that's why we got the negative sign there. All right, let's see. Part C asks us, if the magnetic field is not turned off, at what angle should you rotate the circular surface so that the magnetic flux passing through it is 0? Well, let's look at the equation again. So another way you can affect the magnetic flux here is by adjusting the area or by changing the orientation with the angle phi. Let's go ahead and look at that picture again. Okay, so here's the picture again, and let's remember that this does have magnetic field vectors pointing up here. So we've got these guys all over the place. And the question is, if we want to have the least amount of magnetic field lines pass through to get to, in this case, we want 0 magnetic flux, which way should we rotate this? Should we rotate it that way? Should we rotate it that way? Well, another way to think about it is how do you rotate the normal line, that way or that way, right? Same idea. Well, clearly if we rotate it down in this direction, then more field lines are going to pass through. They're going to be going right through the loop. So that's going to be making the angle phi rotate this direction. It's going to be a 0 angle, and of course you put a 0 in there, you get 1, cosine of 0 is 1, you get the max magnetic flux. Well, we don't want to do that. We want to go in the other direction here. We're going to rotate it in this direction so that it's going to come up and be basically just like this, the loop, and you can see the magnetic field lines aren't passing through. The new normal line in that case going to look like this, and the angle between the magnetic field and the normal line in that case, if we draw the new B field at that position, we're going to see that this guy here, this is a 90, right? And if we put that into the equation, phi equals B A cosine of 90 degrees. Cosine of 90 degrees is 0. So we want to set that angle, as we just saw, phi equals 90 degrees for the flux to be equal to 0. Now, it's important, as we showed in this example, to be able to calculate the magnetic flux because we're going to use that extensively in Faraday's law.